Welcome to figuring out how to calculate a column capital. So let's see what we're even looking at here. I'll move this into the center. So we are within concrete and we're within concrete formwork. So this is still using Pythagorean and trigonometry, quite a bit of it. And it's really not that different than what we've done in the previous trigonometry videos. It looks like a whole lot more because we now have three drawings of what we're actually doing, and we're going to use all three of them to figure everything out. So first, we have a 3D view of this column capital. So think commercial construction. This is a concrete column, and we have this capital, basically an upside down cone at the top to disperse some of the weight, and sometimes just to make it look pretty too. Then we have a cross section. So imagine it gets cut in half, kind of like an elevation view, and it's giving us some dimensions and numbers. And then here we have a plan view of the flattened frustum. So that's taking this and splaying it out flat on the ground. And this is where we're going to do the calculations for our arc length, for our chords. This is where we find the included angle, the radius, which is the hypotenuse, right? Just like we've done before. Let's have a look at what we're looking here. So for the capital shown, calculate the various dimensions required to lay out the frustum. So this is what we want to calculate so we can lay it out so we can actually go ahead and build it. The frustum will be assembled in two pieces. Let's highlight that, two pieces. All of these worksheets are similar but different. Sometimes it'll be 4 pieces or 6, so make sure you read the text and highlight the important parts. It's to economize material usage, great. And for each section, we want to calculate the following. Wonderful. So we have the included angle, we have the radius to the outside arc, so out here, the radius all the way to the outside. We have the chord length for the outside arc, so that's out here. We have the offset for the outside arc, so between the chord and the arc. Then we have the radius to the inside arc, so that's for here, this guy right here. We have the chord length of the inside arc, that's this fella right here. And then the offset of the inside arc right here. So that's the same math as we've done before. This should sound pretty familiar. The only tricky part is finding some of the numbers that we can even work with in this here. So just to make it not necessarily challenging, but interesting, we have a few questions here for real-world application. So let's have a look. The formwork is shown on the left side of the cross section. So right here consists of 9 mil form ply for the deck sheathing and collars. So that's right here and here, right here and here. And we have a sonotube. Sonotubes are always the circular ones, often made out of cardboard or sometimes other materials that are a little bit more sturdy for big columns like this. They're 5 mils thick, and then we have 38 by 89 joists, so that is a 2x4. And then 10 millimeter plywood for the frustum soffit. So that's this fella right here, the skinny one. With this information, at the end, we're going to find the joist length, long to short. So from our long point to our short point, we're going to find our miter cut angle for the end of the joist. So we can go to the chop saw or a skill saw and actually cut them and make everything nicely fit and snugly. And then we want to find the diameter of the circle that we're going to cut in the deck ply, measured at the top side of the sheet. So that's where we're going to work with the numbers up here. So we can cut a big old circle into it so that everything fits nicely and will look really good at the end. So let's not worry about these just yet. I'm going to move this over. We have our SOHCAHTOA as usual, so we can blot out the one that we're trying to find to make that easy for ourselves. So first step. Before we can even find the included angle for each segment here, we need to find the radius, right? In the past, we've used so to find our angle with our hypotenuse, and this is our hypotenuse, right? This is the radius, but we don't have that given to us. In other questions, that's been given to us already. So let's figure this out. Step one, we want to find the radius. First, can we find the circumference of our whole circle? As we find the radius, we can also find the arc here of our segment. So way to do that is looking at our cross section. It looks like our diameter is 800 across. So first we want to find the circumference, and that's from the 3D view, and that's important to remember. Circumference 2 pi r as usual. Diameter here is 800, which means radius is 400. And that's from here to there, right? Getting us across there. 2 pi r, so 2 pi, half of 800 is 400. Let's punch that into the calculator. And I'll move the calculator in and out as we go. So 2 times pi times 400. 2,513.3. That's important to know. Awesome. Now, can we find the arc for each segment? We have two segments, right? The circumference of this whole column is this right here. Because it's flattened, as it's flattened and you bring it up, it comes together. So this whole thing actually represents this whole circumference. So to find the arc, we take our circumference, 2513.3, and just divide by 2, right? Because we have two segments. Divide by 2, 1256.6. And we can put that in here. Arc 1256.6. Cool. That's good for us to remember for later. Now, radii, outside radius. Let's have a look here. I'll move my calculator. Let's look at our cross section up here. Can we turn this sort of shape into triangles? I say yes, we can. We can pop that down here, that down here. Now, all of a sudden, that looks like something we can work with, right? We can kind of pop this over here as well. So let's fill in some numbers. 550 is our up and down number. I'm just going to write that in here so that can make sense for us. Now, can we find out this number? We can, right? We have 800 is the whole diameter, and we can see here that at the bottom, that's 300. So 800 minus 300, so in my head, 500, divided in 2, because we've got one on each side, should give us 250. Now, can we find out the radius? Radius being the hypotenuse right here. We can, right? A squared plus b squared equals c squared. Pythagorean. So let's punch those in. We have 250 squared plus 550 squared, and that will get us our radius right here. 250 squared plus 550 squared, square root, don't forget, will give us 550 for our outside radius. Wonderful. And I completely lied. I don't know what I punched into the calculator, but let's get rid of that. I don't know what I punched in. It's 604. 250 squared plus 550 squared square root equals 604. So let's fix that up here. 604. And that's why it's so important to double check what you're punching in and see, does that make sense, right? I wrote down the 550, not thinking about it between reading and writing, and then I looked over seeing the 550, and there's no way that the hypotenuse of this triangle can be the same as this side. And I purposely leave these mistakes in my videos. It's not just that I don't want to trim and cut them. I just want to show you that that is super normal to make mistakes and just remember to notice and to see what's happening. And then you can fix it and then you can use your brain to do that. Okay, great. So we have our outside radius. How about our inside radius? It looks like there may not be an easy way to figure this out, but we have something given to us here. And what if we just continued these lines down here to turn this into a vague triangle? And then we could cut this in half so we can have another right angle triangle that we could work with. So if the whole width at the bottom is 300, divide by 2 would make that 150. Now to find out the inside radius, there are a couple of easy ways to figure this out, and I'll show you both because there are always so many ways to do math. And it's sometimes good just to know 2 or 3 different ways so that if your brain shorts out, maybe you'll remember one of the other ways. Let's see. So we have a triangle here, we have a triangle there. They are part of the same big triangle, so the proportions should be the same. Can we compare this triangle to this triangle? And what we're trying to find out here is the radius or the hypotenuse. So we can do ratio and proportion, and we always want to compare like to like. So here we're going to have a side over the hypotenuse. Okay, so we have a side, 150, over the hypotenuse, and that's what we're trying to find, right? That's the inside radius equals 250, and our hypotenuse is 604. What we're trying to find here is the hypotenuse on the little one, which is our inside radius. So punching that into the calculator, 150 times 604 divided by 250, 362. And that sounds right, 362. Awesome. Nice. Inside radius. Now, can we find out our total radius? Right, so inside radius, that's what we figured out here. This guy, 362. And our outside radius of 604 is this fella right here. Oops, 604. Now, can we add them together to create our full radius? Of course we can. Total radius is our outside radius plus our inside radius. Right, outside radius up here, 604, plus our inside radius, just figured that out, 362. 604 plus 362, 966. And we can write that down here. That's our full radius of the segment, 966. Check it. Radius to the outside arc. Can we punch that in now? Yes, we can. 966. That's this guy we just figured out. Radius to the inside arc, can we figure that out? Do we have that? Yes, we do. It's the inside radius that we figured out right here. So 362. Just nice to kind of start checking things off the list, right? Okie dokie. I want to show you a different way to figure out the inside radius or even that hypotenuse here. So I'm going to draw a line. We're figuring out the same thing here, just a slightly different way. Going to draw out this triangle. Pop in those numbers. So we've got the 550. We've got the 250. And what we could find out right now to then find out the radius down here, so we could find out the angle. Right? And we're going to need that later as well, but it's just a different way to get there. So let's see. To find out this angle, we have an opposite side and an adjacent. Opposite and adjacent leaves us with TOA. So if we're trying to find tan, it's opposite over adjacent. T equals opposite over adjacent. And remember, you always have to take the inverse of tan. Punching that in, 250 over 550, inverse of tan, 250 over 550. So second function tan, 24.443 degrees. So that is this angle right here. Okay, which is the same angle down here. It looks different because my drawing is not as nice, but it's the same one because it's part of the same triangle. Now from here, with this little triangle, if I draw that out as well, if we're still trying to find our inside radius, that's what I'm trying to show you here. The only number we actually have given to us is the 150. Right? If we kind of forgot we could do Pythagorean or that we could do ratio and proportion like we did here, well, do we know this angle? Yes, we do. We just figured it out. 24.443 degrees. If I wanted to find the hypotenuse, what could we use? We have an angle, we have an opposite, and we're looking for the hypotenuse. Looking for the hypotenuse means we're already in so or ka, and we're in opposite, so we're within so. We're trying to find the hypotenuse, so it'll be h equals O over S. H equals O over S. We'll pop in those numbers. Opposite 150 over sine of 24.443 degrees. 150 over sine of 24.443 degrees gets us 362. Check that out. And depending when you're working with angles, I already left 3 decimal points. If I had left it in the calculator, here we come to 362.5. It would have come to 362.3. You know, it's half a mil here or there. That will be just fine for our calculations. But that's all I wanted to show you. This is the same inside radius as we found here. This angle we can actually use later for our formwork to find the angle that we need to cut our joist with. But we'll talk about that more later. So just different ways to get to the same conclusion, just in case the brain stops at some point. Okay, so we've come to our total radius and our inside radius. We've popped those in. Now, step number 2, we actually want to find the included angle. And we can find several things in this step. We're going to find the included angle. We're going to find the outside chord. And we want to find the offset. We're going to check mark a bunch of things off of this list. Let's make a drawing, shall we? I always think that these look like an ice cream cone. So I do these videos or do this kind of math, and then after I'm always hungry. There we go. So while it's drawn a little bit smaller, not quite as wide, that's what I just drew, right? This segment right here is this segment right here. So let's pop in the numbers we do know. We know that the radius is 966, and we are trying to find the included angle. And the included angle is always the full angle. And when we do our mathing, we want to use the small one or from half of it, and we'll call that the working angle. Now, can we use our circumference that we've already figured out, right? We already figured out the circumference of this. But the radius that we used was 400 coming from the diameter of 800. Our radius now is 966 because it's out on the flat. It's not actually put together. So we need to re-find our circumference on the flat. And it's still 2 pi r. That's never going to change. So we can pop in that number. 2 pi and our radius that we figured out, 966. 2 times pi times 966. 6069.5. Okay, so that is our full circumference of the circle here. Now, to find our included angle, we can compare our arc to the circumference of the whole thing, of the entire circle. So ratio and proportion again. Oops, partial over full. Just what you want to watch out here for is that you always want to compare apples to apples. So partial to partial, full to full. So watch this. We can compare our arc length to the circumference of the whole circle, right? Because now it's on the flat, right? You can see 6,000, this is 1,200. So the circumference was on of the entire circle on the ground. And then we're going to do the same on the other side with the degrees of a circle. So arc length, 1256.6 over the full circumference. We want to find the included angle, right? The angle of one segment. And we know that one circle has 360 degrees in it. Cross multiply. 360 times 1256.6 divided by 6069.5, 74.533. That is the included angle, 74.533 degrees. That is the whole included angle. Let's have a look. Included angle for each. Can we fill that out now? Yes, we can. 74.533 degrees. Wonderful. I always just like to write down what our working angle is. Which is this guy divided by 2, right? Because that's the included angle of the whole segment. But when we're breaking it down to our individual triangles, we're only working with half of it. So working angle. So just divide by 2 gets us 37.266 or 26, yeah, let's call it 266 degrees. So that is the angle that we will be working with. Great. Wonderful. Now, can we find out the next thing, which is the chord length for the outside arc? Well, now that we have an angle, and we have a hypotenuse, which is our radius, we can figure out half our chord. How do we figure that out? Let's have a look. We have an angle. We're looking for the opposite side, and we have the hypotenuse. Looking at our SOHCAHTOA, hypotenuse is included, so we're already here, and we're looking for the half chord, which is the opposite. Marking that one out, looking for the opposite, leaves us with sine times hypotenuse. S times H, popping in those numbers, so sine of 37.27. I'll just shorten that by 1 so I don't have to write quite so much. Times our radius or hypotenuse of 966. Punching that into the calculator. Sine 37.27 times 966 gets us 584.9. That is half the chord. Now for our full chord, we just multiply that by 2, right? 584.9 times 2 times 2, and we'll just round now, so 1170. And chord length for outside arc. That's the one, 1170. Now we want to find the offset. That is from here to here. That's the offset here in red. How do we figure that out? Well, all the way from the center, all the way to the outside of a circle, anywhere within the circle is always the radius, right? We're still working within a triangle here, and we could call this A, right? This is a triangle side, so if we take the full radius minus the side that we could figure out, then that will get us the offset. How do we figure out A? Well, thinking about Pythagorean, we have C and we have B, right? We have the hypotenuse and another side. We also have an angle, so you could use TOA or CA as well. Whatever, really, you can use any of them. Whatever it makes sense in your brain at the moment, you can do as long as you're using the right one and you're punching in the numbers properly. I'm going to go with C squared minus B squared, Pythagorean, so 966 squared minus half the chord. This is a very easy mistake. If you're writing a multiple choice math quiz or this comes up, the wrong answer will be there if you've continued working with the full chord here. Okay, so just be really careful, and that's why you write everything out and you highlight things as you go so that you can make sense of the numbers you wrote down. So 966 squared minus, sorry, there's a bit of a glare, 584.9 squared equals second function square root here, 768.8. That is A. Okay, A being this guy right here, from here to here. So now radius, 966 minus A, we just figured it out, 68.8, gets us 966 minus, if you have this kind of calculator, you can see the alpha here, that's blue, and at the equal sign down here, there's an ANS for answer. So if you pop in the alpha and then answer, if you hear my dog barking in the background, my apologies. No, I lost my train of thought. Anyway, usually you could use your answer and continue doing math with that. But let's just repunch it in. 966 minus 768.8 should give us our offset of 197. There must be some stranger danger at the door. Okay, offset 197, offset to the outside arc, 197, right here. Wonderful. Excellent. So we are completed with our outside measurements and calculations. Now we are on to step number 3. We are looking for the inside chord and the offset. Inside chord and offset. There we go. Now, we are still working within the same triangles, right? We're just shrinking everything down a little bit. So we're just going to draw ourselves another picture. Another ice cream cone. There we go. Draw that in half. Now, just remember, we are looking for the inside, so we want to use our inside radius. That was the 362. We're still working with the same angle, though. That was the 37.27 degrees. Now, to find the half a chord, same thing as before, right? So now we're just duplicating just with the different numbers. We have our angle, we have the hypotenuse, so we're using so. Half the chord is the opposite, so opposite equals S times H. Punching in those numbers, we've got sine of 37.27 degrees times 362 should give us the half a chord. So we're punching it in, sine 37.27 times 362. Gives us 219. Awesome, that's half the chord. Now full chord, 219 times 2, right? Because half the chord is only half. We want to know the full length, so times 2 gives us 438. Awesome. Can we pop that in here? Chord length of the inside arc, 438. Awesome. So on this picture here, that's the one we just figured out right here. Chord of the inside arc. Now next, we need to find the offset. Just as before, offset is from the circle to the edge of our chord. And offset is still the radius minus A. I'm going to call that A as well. Can we figure out A? Yes, we can. Pythagorean. C squared minus B squared. Popping in the numbers. C is 362 squared minus half the chord. Again, making sure you're using the right number. 219 squared. 362 squared minus 219 squared, square root, gives us 288. Oops, 288 right there. So that is A. Still have to do the math here. So radius, 362 minus A of 288. 362 minus 288 is 74. And because there are so many steps, it's so important to write out what you're doing and write it out so that you don't accidentally say, oh, the offset is 288. That's what I just figured out. No, it's you figured out A. And then you still have to take the radius minus your A to find the actual offset. So that's this fella right here. Okie dokie. So that is all the math for our chords and arcs and offsets. So let's move this up a little bit. And now we're looking into our formwork. So next one we're going to find out is our joist length. Cross to make that a little bit Clear. What are we talking about here? Joist length, long to short. So looking at the cross section up here, we want to find the measurement from our short point here to our long point right here. Now I'm just going to draw this out to make it a little bit more obvious. So this is our plywood, 19 mils, right? That's up here. It's a little faint, but you can see it. Then we have our joist. And then we have more plywood down here. But looking at our drawing, this line here comes, the measurement of the 550 comes to the top of this plywood. So I'm just going to ignore it in my drawing. What we are trying to find out here is this. The length of the plywood on the angle. So if we're looking at our triangles and measurements, we have a full height, right? From the bottom here, top of this plywood to the top of this plywood. That's 550. Right? So from here to here, that's 550. We know that this is 19. Do we know the length from the very top here to the very bottom? So from the very top to the very bottom, if we look on the other side, this is the radius that we figured out before, right? So that's the 604, and it goes from here to the top of the plywood. Now our joist fits in between, right? It fits underneath the plywood. So we have to take away from the 604 it's not really the diagonal, but the angled length of the plywood because it's on an angle, right? The whole measurement is here. If we only took off the 19, well, that doesn't quite work. So again, can we compare triangles? Yes, we can. And we always need to compare same to same. So if we're doing a comparison here, think about what we could figure out. We have a height given to us, a total height, and we have the plywood height, right? We can call that a vertical. And then we have the hypotenuse, the full hypotenuse, over a partial hypotenuse. And that's what we're trying to find out. So we're going to go vertical over hypotenuse. That's how you spell it. Oh, with an E. There we go. And this right here, we're just going to call it AP. So the angled ply length or thickness, whatever makes sense in your brain. It's all the same thing, whatever you want to call it. Okay, so vertical, we have 19 for the plywood, and we want to find our AP. How about the big triangle? We have 550 over our radius of 604. See what we did? So drawing this out in just something bigger where we can make sense of what's where just really helps, especially adding some different colors. So cross multiply and divide. 19 times 604 divided by 550. We'll call that 21. I challenge you to cut off 20.8 mils. So the joist length then is 604, right? Our full length minus the 21 mils minus the angled length of our plywood. That should give us 583. So you can pop that in here. 583. Cool. Now the next one is the miter cut angle for the ends of the joists. Miter cut angle. Well, for this one, we're working within this here as well. We already figured this out in the very beginning when I showed you the different ways on how to figure out that inside radius. Let's draw this triangle out. And this right here, that's really the angle that we're trying to find that will represent the same angle that we would cut our joist at. Let's punch in our numbers. So at the top, we have 250, we have 550, and we have our 604. And what we're trying to find is our angle. Really, you can use whichever one you want because we have all the numbers, so you can use SOHCAHTOA or TOA. If you have the chance to use the numbers that have been given to you from the very beginning, I would use those just in case you did something wrong here. You never know, right? That way, at least you get full points for some of the answers, just in case you did something wrong along the way. So if we're using the opposite and adjacent, we would be working within TOA. Looking for tan is opposite over adjacent. Opposite over adjacent. And remember the inverse of tan. So 250 is the opposite over 550. Inverse of tan, 250 over 550. Second function tan gives us the 24.4 degrees. That's this angle. That is this angle. That will be the angle here that when you're cutting your piece, that's what you'll set it to. The chop saw or the miter saw or using your speed square to cut it at 24.4 degrees. There we go. So on this last one, we are figuring out our plywood, circle, diameter. So right here, oopsie, diameter of the circle to be cut in the deck ply, which is the 19 mil plywood measured at the top side of the sheet. Now, this is a little bit of a trick question because we want to find that angled thickness of the soffit plywood. That is 10 mils. And that is the extra measurement or distance we're going to add to the circle we're going to cut into our 19 mil plywood right there. Okay, so we're going to do the same as before, vertical over hypotenuse. This time we're using the 10 mil plywood because that is the extra distance on each side that we have to go over our angled thickness of the plywood equals our height again, 550, over our hypotenuse of 604. Now cross multiply and divide. 10 times 604 divided by 550 gets us 11. To find the full distance, 800 plus the 11 on each side. 800 plus 11 plus 11, 822. And that is the diameter of the hole that we need to cut into this sheet of plywood right here. And that is it. Now remember, when you go through this, whether you get a worksheet like this or you just get a worded question, you can draw all of these out for yourself, right? Always take the triangles that you're trying to work with, or take a bigger shape and turn it into smaller triangles. As you go, draw them all out. Write out, what are you trying to find out on this at this point right here? And remember that the circumference and radius of the piece in its 3D real-world form is different than the radius once it's on the flat. And to find the arc and the included angle, you need to work with the radius on the flat. And then you just work your way through, figuring out one thing after the other. And if you ever lose your brain, you know that there are several ways to do everything. And if everything is lost, just go back to the beginning, reread the question, refigure out what you've done and where you have to go next. And then you should be in pretty good shape.